Swayam Prabha. Digital India. Educated India.
In the last few lectures, we considered the processing of solar radiation and calculating the optical efficiency or the transmittance absorptance product as applicable for flat plate collectors. The time scales had been small like an hour and large like a day or even the monthly average day. Today, we shall go in detail with the theory of flat plate collectors. First, we shall deal with the liquid based flat plate collectors. Why I said in general liquid based is it may be water in general, but it could be an antifreeze solution too to take care of colder climates. We already have gone through the basic collector configuration, the idea being to make the absorption process of solar radiation efficient and less emission and less of convective heat losses, which typically has an absorber plate with tubes as shown here. They can be soldered or welded to the bottom of the absorbing plate, and this is housed in a box, and the bottom is insulated so that the bottom conduction losses are minimized, and top will have one or two, at times though rarely, 3 glass covers, so that convective and radiative losses are minimized. Other configurations are possible. This fin and tube arrangement I have shown in A is nothing but the same. The tubes are attached to the bottom, and you may characterize the system to be comprising of a top loss coefficient and bottom loss coefficient. In general, overall loss coefficient will be equal to the top loss coefficient plus the bottom loss coefficient, though it may not be true all the time. We will see the exceptions a little later. Now, the absorber can be also having the tubes on top of the absorber plates like this, with the argument being the blackened absorbing tubes will be directly exposed, consequently they will absorb more, transfer heat to the fluid more directly. This is the configuration B. You may also have a configuration C, where the tube is in the middle, separated by a flat plate, which we call the fin little later, so on and so forth. Again 1 or 2 glass covers and you have the box with an insulation. These are the fin and tube type of absorbers, with the tube arrangement being slightly different one from the other. each one has its own advantage or disadvantage, and the expressions that we are going to have, they slightly differ. The performance may not be all that much different from one thing to the other. It is a question of manufacturing convenience. Now, you can think of other configurations also. You may have the entire absorber plate with a sort of serpentine tube arrangement soldered or welded to the absorbing plate and goes out. The fluid at low temperature may enter here, may leave here. This is a serpentine absorber. The difference between these two is the total flow rate is divided equally among the number of tubes in the configurations we have shown earlier, and in this case the entire flow goes through the tube. So, this may lead to a higher pressure loss, though there may be some other advantage in terms of heat exchange. Now, if we want to make an analysis, we should know in general the temperature on the absorber as a function of x and y, where we have shown that if I may show the detail that this may have an inner diameter and an outer diameter di and do, and this is soldered, welded with a bond material, so that the thermal contact is good and the heat is transferred towards the fluid. Now, if I call this x, the type of elements something like this, half a fin to the left and half a fin to the right of a tube is a repetitive element. So, this may be called x direction and this may be called y direction, where you have these tubes running perpendicular to the plane as we have shown here. Next is qualitatively we can see, if we plot the temperature, you will have something like this. This will be the middle of the mid plane of the plate, and this is the tube region, and this is at any given x, and this keeps on increasing as you go in the direction of y, and I will have again a picture something like this. In other words, in the fin or the plate region, the temperature varies with a maximum at the middle of the plate. If this is the element I am considering, this will be, this is the T max, and the uniform portion pertains to the tube. So, in a single dimensional plane, if I plot temperature T versus this is the tube, this is the fin sheet rather, this is what I have, this is at any fixed y. The same thing if I consider a fixed x, it will be increasing. So, to give you an idea, if this is one tube where the fluid is entering with T F I and it will be leaving at T F O, if I plot in the tube region, it will start at TFI and exits at TFO. The location can be chosen not only the tube, but also anywhere on the plate in general. This is Y and T, this is on the plate. This temperature will be higher than the temperature on the tube, because the heat is being transferred into the tube from the plate region. So, in general my temperature is a function of x and y, y being along the length of the tubes or the collector and x being across that. Now, we briefly mentioned that the useful energy gain for a collector of area AC can be expressed as transmittance absorptance product multiplied by the solar radiation falling on the collector minus overall loss coefficient multiplied by, I will pick up a mean plate temperature to represent the entire absorber plate. In other words, it is a single node analysis. We consider the entire flat plate to be at a temperature TPM. This, of course, for reasons we already mentioned, has been modified as multiplied with a efficiency factor f dashed tau alpha times I t minus U L. Instead of TPM, I choose TFM minus TA. This gives a little more clear idea about the collector. If TFM is pretty close to TPM, we can say that the collector is more efficient. In other words, it is able to transfer the energy to the fluid to reach almost the plate temperature. Then this factor f dash will be close to unity. So, this f dash is called the collector efficiency factor, which we have already defined. And even to avoid the uncertainty of defining TFM, QU can be expressed in terms of the inlet temperature of the collector. This is a single point temperature. So, there can't be any ambiguity about it, and the factor Fr we already defined as heat removal factor, which is in a way analogous to your heat exchanger effectiveness. So, we recall the definitions of f dashed, the collector efficiency factor, and Fr, the heat removal factor, as the ratio of actual energy gain, I write in brief, by energy gain if the collector is at local fluid temperature. Similarly, Fr is defined as actual energy gain by energy gain if the collector is at collector fluid inlet temperature TFI. Right. In other words, this is the temperature which causes the minimum of the losses and hence the maximum possible energy gain. Now, before we proceed with the analysis, we make a large number of assumptions the list of assumptions one can really remember, but the implication is very important, particularly in solar collectors. Often in heat transfer we make the assumption steady state etc., but in the case of solar collectors and in general environmental systems, that steady state has got a implication and a deliberate assumption. First is steady state performance. We are going to obtain the performance of a solar collector, liquid based for the time being, under steady state conditions, which means things do not change with time, but we know, for example, IT changes with time, and then you have got T A, ambient temperature, also changes with time, and even tau alpha changes with time, being a function of angle of incidence. And if in particular, if you want to be very specific, even the overall loss coefficient may change with the time because of the temperature dependence. However, we assume the performance with steady state. In other words, we are trying to obtain what shall be the useful energy gain if a certain intensity of solar radiation or on a short term scale IT remains fixed. So, there had been sufficient warm up period and the collector has reached its steady state, and if everything else continued to be so, what will be the useful energy gain? That is what we are going to do, even though we know that solar radiation is going to change with time, and hence we may calculate n number of times depending upon hour or half an hour, each being steady state and the subsequent hour being a continuation of the previous steady state. Of course, the second one is construction is of sheet and parallel tube type. In other words, if I show as a sort of skeleton, here is one pipe, a series of pipes are joined to this, and this entire thing is on a plate, welded or soldered as the case may be in the collector box. Now, next assumption rather, headers cover small area and can be neglected. So, there is always the question, what is the area AC? Is it the glass cover area, or is it the total box area, or is it the absorber area, and does it include the headers or not? What are headers? Headers are those things that bring in the fluid into the collector, from where it is distributed through the relatively smaller tubes, as we have shown earlier. There is a reason why the headers are larger and than the so called, this is a header and this is a riser. So, this tries to provide a uniform flow into the risers. We shall see little while later why its larger diameter helps. And there is no absorption of solar energy by covers in so far as it affects the losses. So, if T c is the cover temperature, it is a result of whatever convection is taking place from another cover or the plate and not necessarily the absorbed energy. In other words, we will consider the solar radiation to be transmitted through the glass cover or reflected and not absorbed. The temperature increase is not due to absorption, but by a convective heat exchange only. The headers provide uniform flow to the collector tubes. Now, I shall simplify this. This thicker line is my header and these thin lines are my risers. They are connected over here like this. Again there is another header. So, the assumption is these headers provide uniform flow. So, if there is m dot entering through this and this will be m dot by n through each if n is the number of tubes. So, if the header is larger, delta p across the header is negligible compared to delta p across the riser. So, consequently, you will have almost the same head available for the tube number 1 to the last tube. So, they provide a uniform flow, or alternately if you take m dot to be inputted over here, this will be coming out as m dot and not this. If you choose the second alternative, it enters on the same side and leaves the same side, then there is likely to be a short circuit and most of the flow will be going through first few pipes rather than uniformly up to the last one. In addition to providing a negligible pressure drop, thereby providing a uniform flow, you balance the path length of one tube plus the header and the last tube plus the header. Here is a larger portion. Somehow delta p is more or less the same, trying to provide uniform flow to the tubes. There is one dimensional heat flow from covers. What essentially it means is that if this is a cover, this is from cover 1 to cover 2 and I can consider it to be at single temperature Tc2 and Tc1. Similarly, there is one dimensional heat flow from the back insulation. So, in general I can say there is only one dimensional heat flow either to the top or to the bottom. The covers are opaque to infrared radiation. So, if the covers are opaque to infrared radiation, please remember that the solar radiation effectively is within the wavelength of 0 to 4 microns, whereas after the plate is heated the temperature may be 100, 120 and the corresponding lambda max T, lambda max may correspond to much higher than 4 microns. So, that will be in the infrared range and the covers are opaque, precisely creating what is called the greenhouse effect inside the collector. Then negligible pressure drop through a cover. If there is a thickness for the glass, we do not say this is at Tc1 and the top is at Tc1 dashed. We assume Tc1 equal to Tc1 dashed. In other words, the temperature across the glass plate is uniform. This is an important thing, all of you should pay a little attention. The sky can be considered as a black body for long wave radiation at an equivalent sky temperature of T sky. So, the radiation leaving as a loss from the solar collector will eventually see the ambient at T A, then the loss is from whatever is the glass cover to the ambient temperature. But what we are trying to say is the long wave fields T sky, which is not necessarily equal to T ambient. We will give a simple example. Suppose you measure the temperature of the ambient and the temperature of water in a bucket. The water in the bucket will be at a lower temperature in the evening or night, though it may be little higher than the ambient temperature during daytime if it receives solar radiation. Why does in the night the temperature be less than the ambient temperature? If that is true, there will be a heat transfer from the surrounding ambient to the fluid until the temperature becomes equal to ambient temperature, or it is losing heat to a temperature not the immediate surrounding at T A, but to some other far off place which is at a lower temperature. That is what we call the sky temperature T sky. So, temperature gradients around the tubes can be neglected. Now, in this type of analysis, we do not worry about d d theta, d t d theta is 0. It does not change in the peripheral direction of the particular tube. So, entire tube is at uniform temperature. Now, this is a what shall I say, one very significant feature. The temperature gradients in the direction of the flow and between the tubes can be treated independently. That means, dt dx and dt dy can be treated independently. If you remember, if we treat t as a function of x and y, so I have a partial derivative of dt by dx and a partial derivative of dt dy. Now, what we are suggesting is that this changes in the x direction be treated independent of the changes in the y direction. So, in a mathematical language, a two-dimensional problem is treated as two one-dimensional problems. The consequence is that we have two ordinary differential equations, one in the direction of x and the other in the direction of y, and they can be solved independently. Properties are independent of temperature, and this is a very common assumption in heat transfer and fluid mechanics, and as long as the temperature changes are not too large, one can assume this, and loss through front and back are to the same ambient temperature. So, if this is my solar collector with some slope beta, this will be to the top loss, this will be my bottom loss. So, some people argue if this is T A and the bottom of the collector will be at some T A dash, generally T A dash being less than T A. So, this is a shaded region. So, the back losses will be in principle different from the temperature to which the top losses are taking place, but we assume T A dash equal to T A. Dust and dirt on the collector are negligible. So, we assume somebody cleans them at regular intervals. Shading on the collector absorber plate is negligible. So, one thing is the shading because of its own box, like if we have two glass covers, the height of the box could be considerable compared to the level where the absorber is mounted. So, this may cast a shadow depending upon the time of the day, but we are considering that it is negligible. And similarly, of course, the installation is such that there will be no shadow cast by neighboring building or neighboring structure onto the collector array or the solar collector. So, these are the important things assumptions that are made, a number of them. Main thing is steady state performance, though we know that the solar radiation is changing. Secondly, the two dimensional problem is treated as two one dimensional problems, and uniform flow is provided to the lasers. And in so far as solar radiation is concerned, the glass covers do not absorb the radiation, they are opaque to infrared radiation and the other common things that we have mentioned. So, we recall Q u AC, we may put FR tau alpha times I t minus U L into T f I minus T A. So, we know methods to calculate I t for an hour or a day or a monthly average day, though we may not be able to sum it for other reasons which will come at a little advanced stage. And we also know how to estimate tau alpha comprising of diffuse sky diffuse radiation, direct radiation and the ground reflected radiation, and FR will depend upon my actual energy gain, for which I should find out what is this Q u, upon the maximum possible if the entire collector is at the inlet temperature as given by this term. Okay, it can be experimentally determined or it can be theoretically calculated, which we will see in a little while. But our immediate task is to calculate how do you find out the overall loss coefficient U L. Of course, this may depend upon heat transfer, knowledge, convection between plate to cover and then maybe cover to the ambient. If there is two covers, again cover to cover, and then the radiation from the plate. I shall be using this plate and absorber synonymously. So, when we say collector plate temperature, it is the same as the absorber temperature, and then to the cover, similarly cover to the ambient. So, we have knowledge of convection to find out, to have our heat transfer coefficients, and radiation will depend upon the temperatures, and if you assume that the medium is not participating, for radiation transfer, we can deal with the Stefan-Boltzmann law applied between two surfaces at temperatures T 1 and T 2 or whatever the temperatures is. So, now this is a one node analysis. So, let the plate be at some temperature T p, it could be at a point or a mean plate temperature. Then the absorbed energy is S I t tau alpha, and of course, the overall loss coefficient U L watts per meter square degree centigrade. So, Q u is the useful energy, we will try to put down the thermal network and then calculate overall loss coefficient U L in terms of the thermal resistances. If the plate can be represented by this point, the absorbed energy S equal to I t times tau alpha will be entering, and Q u will be the output, and this is at temperature T p. Now, then let us say the first glass cover for a 2 glass covers, it is at a temperature of T c 1, the second glass cover is at a temperature of T c 2, and then there is the ambient to which my temperatures heat loss takes place. Then again I may have a temperature of T b at the back of the collector, then again a T a. So, now the picture is the absorber is at a plate temperature of T p and incoming absorbed radiation S equal to I t and tau alpha falls on that, and useful energy gain that you obtain will be Q u. Now, rest of it is losses, the difference between these two is the losses, which goes in the top direction starting from the plate to the cover 1 to cover 2 and cover 2 to the ambient. Similarly, from the back of the or bottom of the collector, from the plate temperature to the box bottom of the collector, and then from there to the ambient. So, now we have two paths, a convection path and radiation path. So, this will be having a resistance of 1 by H r P to C 1. So, H r is sort of a radiative heat transfer coefficient and P 2 C 1 is from the plate to cover 1. This will be 1 upon H P 2 C 1, just plate to the cover 1, the convective heat transfer coefficient. Similarly, we have two parallel paths, which is 1 upon H r C 1 to C 2 and 1 upon H C 1 to C 2. In other words, this is a convective heat transfer coefficient between the plate and the cover 1, and H C 1 C 2 is the convective heat transfer coefficient between cover 1 and cover 2, whereas the H r counterparts are the radiative heat transfer coefficients. From here, we have got again a radiative loss H r C 2 to the ambient, then a convective loss by wind, which is 1 upon H w, or you can call it 1 upon H C 2 to ambient. So, this is a wind heat transfer coefficient, or in general terminology from cover 2 to the ambient. At the bottom, there will be simply a conduction given by a resistance of delta x upon k if the thickness of the insulation is delta x is insulation thickness. Do not be confused with the x direction, it has nothing to do with it, it could have been L by k. And then we have a convective loss 1 by H back to ambient and a radiative loss 1 by H or back to ambient. Okay. Now, let me, because this is an important thing to understand, let me recapitulate. An absorbed energy of S equal to I T and tau alpha is absorbed by the plate at temperature T p, giving out the useful energy gain Q u. The loss will be from the plate to the cover 1 by radiation and by convection, and again from cover 1 to cover 2 by radiation and by convection, and you have from the cover to the ambient by radiation and the wind velocity or the wind heat loss coefficient. From the bottom you have a conduction loss through the insulation and again a convection and radiation from the back of the solar collector to the surrounding temperature T A, which we assumed equal to the ambient temperature T A. So, this can be simplified, those two all parallel resistances can be combined into one, and we have a simplified picture. S flowing out at T p, Q u the useful energy gain, this is T c 1 and resistance of R 1, this is T c 2 and a resistance of R 2, I am sorry, this is R 3, T A, this will be R 1. You have the conduction resistance, this will be R 4 and the overall due to convection and radiation R 5 from the back temperature T b to T a. This overall can be further simplified as you have got T p and you have got Q u. The loss is T a 1 upon U L and the incoming radiation is absorbed radiation S. Okay. So, we have to find out U L or 1 upon U L. So, first we shall evaluate these resistances one by one. The glass covers are at temperatures T c 1 and T c 2. Let the emissivities of the plate be epsilon p, cover 1 epsilon c 1 and cover 2 epsilon c 2. So, I can express Q loss top should be equal to H p C 1 into T p minus T c 1. This is the convective loss from the plate to the cover 1 plus sigma T p to the power 4 minus T c 1 to the power 4 upon 1 upon epsilon p plus 1 upon epsilon c 1 minus 1. So, we are treating them as infinite parallel plates at temperatures T p and T c 1, and the corresponding emissivities are epsilon p and epsilon c 1. So, this is the radiative loss and this is the convective loss. So, the same amount of loss should go from cover 1 to cover 2 and eventually to the ambient. So, this can be rewritten as Q loss top H p C 1 plus H r p C 1 into T p minus T c 1. Now, that radiative loss is expressed in terms of a radiative heat transfer coefficient multiplied by just the temperature difference, not the difference of the fourth powers of the temperatures. So, H r p to C 1 is defined as sigma T p plus T c 1 into T p squared plus T c 1 squared by 1 upon epsilon p plus 1 upon epsilon c 1 minus 1. There is no magic. If you just multiply with T p minus T c 1, it will be nothing but sigma into T p to the power 4 minus T c 1 to the power 4 upon 1 upon epsilon p plus epsilon c 1 minus 1. This you have done in your undergraduate heat transfer course in the radiation part. So, now my resistance R 3 is given by one upon the summation of the conductances H p C 1 plus H r p C 1. So, the resistance from the top cover to surroundings has the same form as above, but the convection heat transfer coefficient is for wind across the collector, right. Now, this is R 3. So, what is H w? This is the wind heat transfer coefficient. H w is 5.7 plus 3.8 V, where H w is in watts per meter square degree C and V is the wind velocity in meters per second. This relation is due to McAdams. Subsequently, more recently rather relatively, Wortmann et al. Suggested this H w be calculated as 2.8 plus 3.0 V. Again H w is watts per meter square degree C and V is in meters per second. So, you can see that the Wortmann's relation gives a lower value for H w compared to the value one would obtain by McAdams relation for a given wind velocity. It is suggested that apparently perhaps the radiative loss also has been included in the McAdams relation. So, this is what we so far have introduced the theory of liquid based collectors, flat plate collectors. Basically, they comprise of a sheet and tube. The arrangements can be different. It may contain even one cover or two glass covers. The idea is to find out the overall loss coefficient under a set of assumptions. The assumptions had been mainly the steady state temperature, and the problem can be treated as two one-dimensional problems instead of one two-dimensional problem. And then a thermal network has been written, and losses from the top will be from the plate to the cover 1, cover 1 to cover 2, then cover 2 to the ambient, from the bottom by conduction through the insulation, and then again by radiation and convection to the ambient. So, with this terminology, we also have a relation for the wind heat transfer coefficient proposed obtained by McAdams or Vatmuff, and more recently Vatmuff is being used more often than the McAdams relation because of its expected accuracy, and McAdams relation is maybe provides a conservative estimate because HW is larger. So, subsequently we will go about how to find out UL. We have expressed all the resistances. Now, we need to find out what is the overall heat loss coefficient.